This algorithm is the first capable of estimating global 3D joint locations for two hands despite varying occlusion using only monocular RGB images. There have been previous successes in estimating the canonical pose of a single hand using a single monocular RGB image. This is the first program, to our knowledge, to estimate global poses for both hands. As we are the first to attempt this, there were no existing datasets available for this task, so we created our own synthetic dataset. The dataset we created contains 50,000 random poses, 20,000 random backgrounds selected from 100 different image categories, segmentation masks for the fingers, palm, and forearm of both hands, and annotated 2D and 3D joint locations. Our pipeline consists of four major components: hand segmentation and detection, 2D hand pose estimation, 3D canonical hand pose estimation, and 3D global hand pose estimation. We created an algorithm we call HandSegNet that obtains the segmentation masks and heat map energy of both hands in a single image. The segmentation masks separate the color of the hands and arms from the background, while the heat maps approximate the exact position of the hands. The segmentation masks of the image are then used in an algorithm called PoseNet2D, which uses a convolutional pose machine as its backbone to estimate and refine the 2D heat map of the joints. An algorithm we call PoseNet3D uses the 2D heat map as an input to estimate the 3D canonical hand poses. In order to reconstruct the 3D global pose estimation using the 3D canonical pose estimation and 2D pose estimation, we use the spherical coordinate system because reconstruction in the Cartesian coordinate system introduces rotational ambiguity and depth ambiguity. As we can see in this illustration, as the same hand pose in Cartesian coordinate system moves from the left to the right, the camera will see the thumb when the hand is on the left and the pinky when the hand is on the right. This is due to the rotational ambiguity as the same Cartesian hand pose visually rotates at different global positions. Also, as the hand moves from the left to the right, the z-value of the hand remains the same despite the hand's increase in size as it moves closer to the camera and decrease in size as it moves away. This is due to the distance ambiguity as the hand size in the image does not correlate to the z-value of its Cartesian coordinate, but the absolute distance between the hand and the camera origin. To address these two issues, we use the spherical coordinate system to represent a 3D global hand pose. You can see that as the same hand pose rotates in the spherical coordinate system, its visual representation stays the same. Also, the hand size directly correlates with the radius value, which is the absolute distance between the hand and the camera origin. As a result, the rotational and depth ambiguity is solved when using spherical coordinate system. During training, we generate the 3D canonical poses by spherically rotating the 3D global poses to the center of the view, then applying zero centering and normalization. During testing, we estimate the depth of the hand pose using the 2D and 3D canonical pose information, camera intrinsics, and actual key bone length. Translate the hand along the z-axis to its estimated distance, and spherically rotate it back to its estimated global position, reversing the steps we used to generate the 3D canonical poses from 3D global poses. We show through our results that we outperform methods that utilize additional information for single-hand 3D canonical pose estimation. And we further achieve promising results for two-hand 3D global pose estimation.